Linear momentum. Why is this chapter called linear momentum? Because there's another one that's coming that is called angular momentum. And linear momentum is a vector because you can see it's represented by P. And the arrow on top shows it's a vector, isn't it? What's momentum? It's just the product of mass and velocity. Just the product of mass and velocity. That's about the most important point in this chapter. Momentum is the product of mass and velocity. Is velocity a vector? Yes, it is. And therefore, what would be the direction of momentum? The same as the direction of velocity. As you can see on the screen, if you look at that picture, you see that that object is moving to the right, isn't it? Talking about this object, its velocity is to the right. What about the direction of momentum? What's the direction of momentum? Same, right? So if an object is moving to the north, then the momentum is to the north. Whatever direction it's moving in, that's the direction of momentum. So once again, momentum is the product of mass and velocity. Let's look at the units. Mass is in kilograms. Velocity is in meter per second. If you put them together, you will get the unit of momentum. And so the unit of momentum is kilogram meter per second. Kilogram meter per second. You have to put them together. Okay, I'm saying that the direction again, I'm saying that the direction is the same as that of velocity. I thought if I write too small, you can't see it, so I couldn't make it bigger than this. So velocity is the same as that of direction. Now, is there any confusion about that point? Nothing, right? Momentum is the product of mass and velocity. Now, you may be thinking, why should scientists or physicists declare a quantity called momentum? And you might have a question like, how did they get that? That is the product. Now, this quantity is specifically defined to study collisions. You know what a collision is, right? You know that if you are in a tiny car that is moving really fast and you go and collide with an 18-wheeler, even if it's not moving so fast, you're going to be hurt in the tiny car. Why? Because it's not just the velocity that's important, it's also the mass. Agreed? You also know that when the tiny car and the huge truck is stopped at a red light and it turns green, you try to move off. And always you beat him, isn't it? Because of the huge mass of the truck, it's not easy for that guy to pick up momentum. Are you getting an idea of what momentum is? So it's mass and velocity that are equally important. Okay, now we're going to try to relate this to force. What is the formula for net force that you know? You can talk actually. You need not ask questions, but you can talk. What is the formula for net force? Mass times acceleration. We're going to get it in a new way. We're going to see how net force is related to momentum. So the second point in this chapter is the relation between net force and momentum. You know, that stands for delta P, means change in momentum. So when you have that little triangle there, means change in momentum divided by change in time. So net force is the rate of change of momentum with time. That means how fast momentum changes. Get an idea of this. Don't just be in the math. If the momentum changes quickly, that means the force acting is bigger. Right? If the momentum changes in 0.1 second, as compared to the change in momentum in 1 second, where is the net force bigger? Where the time is smaller. So that is how net force is related to change in momentum. Okay, we know that momentum is mass times velocity, right? So when you take the net change in momentum, you can take mass times change in velocity. Masses are constant, so it's going to be taken out. Isn't momentum mass times velocity? So change in momentum is change in mass times velocity, right? Mass being constant taken out. and then put it back into the equation, delta P by delta T. So you would have that. And what is delta V by delta T? Anybody? Acceleration. So now you get mass times acceleration proved. So for the first time, we have proved Newton's second law, that net force is mass times acceleration. Remember in that chapter, we were just taking it for granted, right? We were just assuming, oh yeah, net force is mass times acceleration. But now you get it. And you have to know how to derive this. It's just 3 steps. I can ask you to do such things on exam 3. Okay, going back over this one more time quickly. The important thing is net force is the rate of change of momentum. Change in momentum divided by time, from where we get net force is equal to mass times acceleration. So let's go on. Impulse. This term is borrowed from biology. I always give this example of somebody trying to prick you with a pin on the back of your neck. What would you do? Would you just turn around, look at who that is, and if that is your friend, you would say, hey, what did you do that? No, you would not. It's an immediate action, isn't it? It's an immediate action. Somebody hurts you, your hand just goes, hut, and if it's your dad, you say sorry after you hit him. Now that's called an impulse. Now what happened during this time? Was the time involved small or large here? Very small. What happened is electrical signals through your nerves went to the brain, and then the brain signaled to the muscle here, go hit him. And all this happened in a millisecond. So that's where the word impulse comes from. How do you apply this to physics? Let's say you're trying to hammer a nail into a wall or into a piece of wood. You take a hammer, and do you do this? Do you just go? No, you don't. What do? You just go. You apply a huge force for a short time. That's what an impulse is. What about kicking a soccer ball? What about hitting a baseball with a bat? Think about the force. Is it small or big in all these cases? The force applied is big, but what about the time of contact? Small. You can think about hundreds of examples. Most of them come from games and sports. Isn't it? So what's an impulse? An impulse is a big force acting on an object for a short time. That is the definition of an impulse. The problem here is, because the time involved is so small, we cannot calculate the force in the usual way. What's the formula to calculate force in the usual way? Mass times acceleration. But the time is so small that we don't have time to calculate the acceleration. That is why they had to define something called impulse. See, when some quantity is big, another quantity is small, what happens if you take the product? It'll become average, isn't it? That's the idea. So impulse is actually the product of force and time. I've written there, impulse is the effect of a force that also depends on time. The effect of a force that also depends on time. And impulse is defined as the product of the net force and the time. Impulse is the product of the net force and the time. But what is the net force in terms of momentum? Delta P over delta T, isn't it? We got that today, delta P over delta T. If you do that, what's going to happen to the delta T's? Cancels out, and you get a wonderful formula there. Now you prove that impulse is also equal to, how do you read this? What is this? Change in momentum. So you have 2 formulas for impulse. 1, net force multiplied by time. 2, equal to change in momentum. Two formulas. Put them together. I put both the formulas together now. There you go. And you have a very important equation. Change in momentum is net force times delta T. How do you find the change in momentum? How do you find the change in momentum? Let's do one problem without writing anything. Let me see whether you can do it. Let's say there's an object of mass 1 kilogram. 1 kilogram. At rest. Are you with me? What's its momentum?
Zero.
Not moving, so momentum is 0. And then after some time, don't worry about the time. After some time, it starts moving at 10 meters per second. What's its momentum now? 1 kilogram moving at 10 meters per second. What's its momentum? 10. What's the change in momentum? 10 kilogram meter per second. What's the impulse? Same. Because impulse is change in momentum, isn't it? That's it. So you take mass times final velocity minus mass times initial velocity. That's it. That's what you mean by change in momentum. Okay. Impulse can be obtained from a graph. If you draw a graph between time and force, time on the x-axis, force on the y-axis, this is what you would get for an impulsive force. Somebody try to explain this. What's the graph? What does this mean? Let's think about me hammering a nail into a piece of wood. Am I applying a constant force? What's the force just before the hammer hits the nail head? What's the force? No, just before it makes contact, what's the force? 0. And then in that millisecond, the force grows to a huge quantity and then drops to 0. Can you visualize what's happening? It's like, so that's why the graph looks that way. What's the force here? 0 there, grows to a huge value, and then, that time, what do you know about this time? Is this small or big? Very small time. During that small time, the force becomes big and then drops. So how do you find the impulse from here? You find the area of the graph. Because product is just the area. Didn't you know that? Impulse is the product. So just find the area of this graph. All right, so the time between which it happened is T1 and T2. What I drew just now, the dotted line, shows you the average force. You know what the meaning of the word average is? What was the minimum force there? Minimum. 0. And there was a maximum, isn't it? So you can see that the average is between the two, not necessarily exactly halfway, okay? That is the average force. So the dotted line shows you the average force. Remember, this is the force axis. So that is the average force. If you take the area there, well, I'm showing that's the actual force. That is the average force, isn't it? The actual force was not constant, but you assume that it's an average force, and you call it the effective force. This is interesting for those who understand. Isn't that the area, actually? But I'm going to take the area another way. Watch very carefully. If I take the area of that rectangle, watch. This one, do you see that? Will I get the same area as this actual thing? The answer is yes. You know why? Because when you take the area of the rectangle, you're missing this part, isn't it? Are you watching? But that is compensated for by these two extra areas by the sides. Watch very carefully. Do you see that? So instead of taking the area of this graph this way, the green one, we can just take the area of rectangle. I'm trying to say that the two areas are the same. Now that means there is a new formula for impulse. Who got the new formula? I already gave you two formulas. How did we start with? Wait, how did we start with? What was the formula of impulse when we began?
F net times change in time.
Okay, it was F net times change in time. But you see that when the force is changing drastically like this, there's no meaning in saying F net. So now we replace the F net with the average force. So now impulse is the average force. I was just average force multiplied by time. I'm trying to give one example. Read your textbook for several examples. If somebody throws a fast ball at you and you have to catch it, wouldn't you pull your hands back? What are you doing when you pull your hands back?
Increasing the amount of time.
Increasing the amount of time, thereby reducing the force. Simple thing. Because the product of force and time is going to be the same. If you increase the time, you will reduce the force. If you decrease the time, if somebody is a fool, instead of pulling the hand back, they will move it forward. That's real foolishness. Now that's obviously the difference between jumping. Let's say there's a fire in your home, let it never happen. But if it happens, and you have to jump, and if you jump onto concrete, your legs are broken. But if you jump onto sand, your legs won't break. Well, it depends on how much sand there is and all that. But what's the difference between jumping onto concrete and onto sand? The time. You hit concrete, the time involved for you to stop is so small, isn't it? You hit concrete and you stop. So the force is big. But when you jump onto sand, you don't stop in that small time. The time is increased. Are you getting what I'm saying? Therefore, the force is decreased. How many examples there are for this? If you increase the time, the force decreases. That's an idea that we use many times. Many times. Even when you step on the brakes, usually the driver doesn't feel it, but the passengers do. Because the driver is holding the steering wheel. You don't feel, you jam, hit the brakes, it's the passengers who feel it. Haven't you heard them shout at you many times if you're doing that? So increase the time so that the force is small. Well, we are almost at the end of this chapter. So if I ask you, pulling hands back when catching a ball, why do you do that? And if you don't answer, I feel so mad and crazy. The last part of this chapter is called conservation of momentum. What is the meaning of the word conserve? Conserve means neither created nor destroyed. Conserve means not changed. That's why we say conserve energy. Don't waste energy. Conservation of momentum. It says here, that's the law. Momentum before interaction is equal to the momentum after interaction. What do you mean by interaction? Anything. Isn't it a collision in this case? All right, take a look at that picture carefully. Let's go. We can draw and write later on. The two cars, do you see their masses? Mass of the first one. Come on. 500 kilogram, moving at 5. So what's its momentum? If you have a calculator, take it out. If you need one, we're just working out a problem. 2500, right? What's the momentum of the second one, the yellow one? What's the momentum of that? 800. So what's the total momentum before they run into each other? Add them both. 2500 plus 800 gives you 3300, isn't it? Okay, that is the total momentum before the interaction, before the collision. Now look at the diagram below. Look at their velocities. Wait, has the mass changed? No, we're assuming that nothing broke off, And what they call, what is it? A fender bender, you know what that is? So, okay. And you have this 4.5 meter per second. What's the momentum of this now? 1800. If you multiply those two, you get 1800. All right, go ahead. Multiply these two. What do you get? 1500. Add them up. What do you get? 3300. So what's the momentum after interaction? 3300. That's all. Is this so tough to understand? No, it is not. The momentum before collision is equal to the momentum after collision. But you have to understand, this is true only if, this is the condition I'm giving you, only if there are no external forces acting. No external force is acting. Did they apply a force on each other?
Yes.
Yes, that's an internal force within the system. What would have happened? Oh, let it never happen. But what would have happened if another car came and hit them? Wouldn't that be an external force? Then momentum is not conserved. So momentum is conserved only if there is no external force. That's a condition, very important. So total momentum before is equal to the total momentum after. Let's get an equation now. Does this make sense? What do you see on the board now? See, because we have two objects now, we have to talk about delta P1 and delta P2. Are there two objects in a collision? So that will be the subscript 1 and 2. Don't we know that change in momentum is force times time? Come on. So the change in momentum of 1 is F1 delta T. What about the change in momentum of 2? F2 delta T. So you have the two equations. Wait a minute. What's F1 and what's F2?
Force 1.
They are the forces they apply on each other. Can anybody give me the relation between F1 and F2?
F1 equals negative F2.
Oh, that's so fast. If F1 is the force applied by the, what was it, blue on the yellow, and F2 is the force applied by the yellow on the blue, one is the action, the other is the reaction, and according to Newton's third law, the action and reaction are equal and opposite. Therefore, what's the relation between F1 and F2? F1 is equal to negative F2. Okay, keep that in your mind. We're going to use that. F1 is negative F2. That's from Newton's third law. Okay, substitute that into this, and we get an equation. So would I get F1 plus F2 is equal to 0? If F1 is equal to negative F2, bring it over to the other side, right? I would get it. And what's F1? Can I write this now? Why? Because time cannot be 0. Isn't it? See, delta, just take a look. Delta P1 is F1 delta T, isn't it? So I could have written F1 delta T plus F2 delta T is equal to 0. And then I could have taken delta T out. Can time be 0? No. Therefore, the only chance is these two should add up to? Well, we have proved it. What's delta P1? What do you mean by delta P1? Change in momentum of first object. Now I'm going to write something down. Change in momentum of the first object. Wait before you copy it down. What does that mean? What is V1 prime? The final velocity of the first object. What is V1? The initial. I'm going to use the textbook notations. You see, that's why it's... So isn't that the change in momentum of object 1? M1. 1 represents object 1, remember. So that's the change in momentum of object 1. Can you fill up the right-hand side? Go ahead. What would be on the right-hand side?
Same thing as with
Same thing with 2. Can we rearrange that now? Okay, I just put plus equal to 0. Wanted to bring that in the next step. See, I wanted it to look exactly like this. You see where I'm coming from? Look at this. Right? So I wanted it to look exactly the same. So that's delta P1. That whole thing is delta P2. Come on. Is equal to 0. Okay. Now I'm going to write equal to. You know, if you try to cram this equation, it looks big. But what is this actually? What is this? Can you give me a sentence for, what do you see here? Can you give me a sentence for that? What is that?
Conservation of momentum.
No. On the left-hand side. Only the left-hand side. What is this? Wow. Come on. Do you see both objects are considered here? Yeah. So what is this? That is the total final momentum. What's on the right side? The total initial momentum. That means momentum is conserved. The total final is equal to total initial. We're going to use that formula a lot. And 2 labs. Based on this, you have 2 labs on conservation of momentum. So that is the equation that you should remember, the last one. That's why it's so colorful. So you look at it. Okay, didn't I mention that there should be no external force? Yes. No net external force acting. There can only be forces between each other or between them. Same picture there. I'm writing that equation one more time. M1v1 prime plus M2v2 prime is M1v1 plus M2v2. We did this, didn't we? 500 times 3, correct? We did that. I'm just trying to show you. Didn't we get 3300 on both sides? Just trying to show that it's correct. That's all. Not trying to show off. So in the lab, you'll have to prove this. Okay. Last, but as they say, not the least. There are 2 types of collisions. One is called an elastic collision. The other is called an inelastic collision. Elastic and inelastic. I think I'm talking about elastic collision here. You know what the difference is? In an elastic collision, kinetic energy is also conserved. Remember kinetic energy? What's the formula?
Half mv squared.
Half mv squared. So kinetic energy is also conserved. In addition to, what is conserved in all collisions? Momentum. Whether it's elastic or inelastic, momentum is always conserved. But what's the additional fact here? If it's an elastic collision, kinetic energy is also conserved. So that means both momentum and kinetic energy are conserved. So that's the difference. Internal kinetic energy. When I say internal, it's the kinetic energy of the 2. Is also conserved. All right, that's a diagram that might give you more sense of what's happening. And the terms. Initial velocities, v1, v2, final v1 prime, v2 prime. The 2 objects collide. Kinetic energy is 1/2 mass times velocity squared, isn't it? So take the, well, on the left-hand side, I have the total kinetic energy after collision. And on the right-hand side, I have the total kinetic energy before collision. I'm trying to drive home that point again. No loss of kinetic energy. That's clear, isn't it? If it's an elastic collision, there is no loss of kinetic energy. But there's a problem. If 2 people run into each other, is that elastic or inelastic? Be careful before you answer. It happens usually when you walk around the corners. Some people run around corners. That's scary. Don't do that. If you run into each other, is that an elastic collision or inelastic? Inelastic. Why? Because you would hear a thud. That sound produced. Where did that come from? A little bit of the kinetic energy has been changed into sound. Come on, do you understand? So most of the collisions that you see around you are inelastic. 2 cars run into each other. Oh, goodness, you hear a lot of sound, sometimes sparks. Where did all that come from? Kinetic energy. You know what I'm trying to say, right? So kinetic energy is lost in all these collisions. So what will be the best example for an elastic collision? Imagine you have a small steel ball. Drop it onto concrete floor. Be with me. Drop it, not throw, drop it on the concrete floor. Will it bounce back? Will it bounce back exactly to the same height as you dropped it from?
No.
But that will be much better than what you do with a rubber ball. Think about it. If you have a steel ball and a rubber ball, now I know you're thinking that the rubber ball will bounce back more. Isn't that what you're thinking? But it's not true. Which is more of an elastic collision? Is it when it bounces back to the same height, or it, silly question, or when it does not? Which is an elastic collision? When it bounces back or higher, that means it's more of an elastic collision because there was no loss of energy, right? If it bounces only to half the height where you dropped it from, that means half of the energy is gone. Does it make sense? So what is a perfectly inelastic collision? Perfectly inelastic is when two objects stick together after the collision. You got to write that down. That's very important. If two objects stick together after collision, then it is completely inelastic. Completely inelastic. If they stick together. That means there is total waste of energy there. Kinetic energy, maximum kinetic energy is lost if they stick to each other. Okay. Elastic collision in 2 dimensions. What is the difference between collision in 1 dimension and collision in 2 dimensions? What? You saw the example before where you had those cars. Okay, look at my hands. Now, if these are 2 objects and then they run into each other and then after collision they continue along the x-axis. That's 1-dimensional collision. So they were moving along the x-axis, right? And after collision they continue moving along the x-axis. Is that what you see normally in life? After collision, do they continue moving in the same line? What happens? It's like they are moving in one line. First, of course, you have 2 objects. You can always draw a line, right? You know what I mean. But after collision, what happens? One goes that way, the other goes. So that is 2-dimensional collision. You got it? But when you look at a 2-dimensional collision, I'm going to show you the diagram. Okay, those are the 2 objects before collision. You see that they're just colliding. See what happened after collision. They go different directions, don't they? The red one goes down in that direction, the brown one the other direction. So now we need to name those angles. We call them theta 1 and theta 2. Masses m1 and m2. Velocity is after v1 prime, v2 prime. Velocity is before v1, v2. Okay, hold on. Get all the terms. So the masses of the 2 objects are m1, m2. Their velocities before are before collision, v1, that's for mass m1, v2 for mass m2, right? And after collision, the velocities became v1 prime and v2 prime, but there are 2 angles involved now. So what do you do now? Let me try to find out from somebody. I've drawn this diagram in such a way that before they were moving along the x-axis, isn't it? Yeah, you have to draw and write, but what's more important is to understand. Are they moving along the x-axis before collision?
Yes.
Okay, so answer this question. What is the momentum of object 1 along the y-axis before collision? What is the momentum of object 2 along the y-axis before collision? 0. Agreed? So what's the total momentum about the y-axis before collision? 2 zeros add up to 0, right? Okay, be with me. What about after collision? Only look at the y-axis. Look at the y-axis. We know that we can resolve this into two components. What is this going to be? M1 V1 prime cos theta 1, right? Okay. And what about this one? M1 V1 prime sine theta 1. Are you getting it? Or do the same thing with this. What will be the x component of this? Wouldn't it be M2 V2 prime cos theta 2? And what would be the y component? M2 V2 prime sine theta 2. So we were talking about the y-axis. So give me the momentum after collision along the y-axis. Go ahead. Which components? The sine components. So what would the equation look like? 0, that was before, right? Is equal to, go ahead. M1 V1 prime sine theta 1 plus M2 V2 prime sine theta 2, right? If you try to cram this without understanding, it's deadly. But if you understand, it's easy. Okay, that was for the y-axis. What about the x-axis? Give me the equations for the x-axis. What is the total momentum before collision about the x-axis? Be careful now. Didn't this have a momentum? It did. What is it? M1 V1. What is the momentum of this? M2 V2. Should be equal to the cos components. Finished. Is equal to what? M1 V1 prime cos theta 1 plus M2 V2 prime cos theta 2. Let's look at the equations. Let's see. Along the x-axis. See, when I say it, it looks like it's so tough and huge. That's it. Along the x-axis. Is that right? Along the x-axis? And along the y? What's on the left-hand side for the y? Okay. You understood, right? Okay. Those are the two equations. There you go. I'm concluding the lecture for this part. I hope this helps. Thank you.